Okay, good morning, guys. So let me tell you a little bit about the assignments. So I mentioned last lecture that one of the grading criteria for this course will be assignments. So I'll tell you a little bit more about it and the kind of topics that you might be doing. So as I said, this is a kind of more of an open-ended investigation. So you're supposed to look into particular problems, and no particular right or wrong answer. You're supposed to just kind of research it towards what you think are the important questions, and then of course I'll tell you also some ideas of what I think are the important points that you should be looking at. So essentially what I'm kind of looking for in these assignments is a kind of level of sort of detail and realism in terms of the problem that you're trying to solve. So I'm not necessarily looking for just, I'm not looking for like the correct answer, it's not that, I'm looking for the fact that you should be doing, calculating something and there's a particular number that you should be getting. It's not really that type of problem. It's more like, you're trying to achieve a task, and there are probably many ways of actually achieving that in practice. Just look at the fact that there's all kinds of different technologies out there, and not everything relies upon exactly the same kind of technology. And but some things tend to be sort of better than others. The idea is sort of you should kind of show what you think are the important ways and the way that you think it should be done. So the kind of topics that I have in mind are, I'll give you just a quick overview of the topics which I'm providing. You don't have to stick to these topics, but usually in the end most people do. So I've got a list of I think 8 or 9 assignment topics, and how it will work is that I'll send up a sign-up sheet this week, and you'll be in groups of 4 so that you basically choose the assignment topic that you are most interested in, and there's maximum of 4, so it's sort of first come, first serve. Obviously, some of you ask, can you work with people that you're familiar with? Of course, you're very welcome to. So you would just coordinate amongst yourselves. You say, okay, let's work on assignment number 5, say, and then you'd sign up for 5. So so let me give you a brief overview of the topic. So the first one is the so-called bottle opener building in central Shanghai, right? It's got a hole in it, right? So suppose as a part of a publicity stunt, NYU Shanghai wanted to shoot an object with a NYU logo from the top of this building through to the hole of this building, right? And you wanted to make it land in the Huangpu River. So obviously this is a kind of a simple sort of projectile motion type of question, but really more importantly, how would you really do this? Imagine you really had to do this. What would you use, and how would you actually achieve this, and how would you do it without causing a major catastrophe where you're gonna throw a very fast-moving object to a major center in Shanghai. So the idea is sort of, to try and make this as realistic as possible so that you could actually do it in practice. Probably it's just way too dangerous to do it in practice, so we're not really going to do it. But it's a kind of a thought experiment of practical problems that you need to sort of solve. Okay. Second one is, what's happened here? Very glitchy. Let me reshare. Okay. All right. Second topic is the Mars mission. So, a couple of years ago when I was doing this course, I haven't taught this in 3 years, but 3 years ago nobody really knew who Elon Musk was 3 years ago, but I think things have changed a lot. I think everybody knows who Elon Musk is these days. So before he was doing this SpaceX venture, actually there's a story where he was trying to pull off this more or less publicity stunt where he was going to buy a missile, in fact a Russian missile, that was used originally for weapons but repurposed into a kind of a rocket. And he was going to send this to Mars carrying a bunch of water and some seeds. And the idea of this was that it would just basically land uncontrolled into Mars, but then some of the seeds would still survive and there would be water, and then there would be plants growing on Mars. So against this red backdrop of Mars, there would be like green plants growing, and then this would be like the biggest publicity stunt ever. Have you heard of this story? No. Anyway, it's true. This guy's pretty crazy. Needless to say, he didn't do this. But he really tried to do it. It wasn't like, funny idea. He literally went to Russia and was talking to Russians of how to buy this missile. So in this one, basically you would do your own kind of calculation of whether such a thing would have been feasible in the first place. Like, could you repurpose like a missile into a rocket that would actually make it all the way to Mars? Obviously a missile is not built necessarily for going into space exactly, but of course there's very similar technologies involved. So, okay, another sort of Elon Musk related one. So the Hyperloop. Have you guys heard of the Hyperloop? Yeah, maybe. Hyperloop is a new form of travel. Again, it was sort of first proposed by Elon Musk. I don't know. He might have again stolen it off somebody, but it's supposed to be. It's basically like this sort of tunnel that you build underground, and it's supposed to sort of bypass all the traffic, of course. So, of course, tunnels can bypass traffic. But it's also supposed to be a new form of transportation because somehow these pods inside these tunnels can sort of levitate more easily. So it's sort of like maglev, but inside a tunnel. And so it's supposed to be a more efficient version of maglev. But nobody really knows how it works exactly. You keep on hearing about it and you say, oh, it's an amazing thing. But when you actually try and figure out what people are doing with it, I think Virgin, the company, the airlines, record company, Virgin, that guy, they also are trying to do this. All these billionaires are now all of a sudden all trying to do the same thing. Have you noticed? They are all trying to do this type of technology because it's supposed to be the future, but nobody really knows what it is. So I think everybody's got a different idea for how it's supposed to work. So there have been people that have been kind of also criticizing this for saying that it's just a glorified subway and it's really no better and it's actually a pretty stupid idea. All the way to the other end of the spectrum where people say it's the future of travel. So the idea is to kind of investigate this and just figure out what the hell is going on and try and see if you can make any sense of it, see if it makes any sense from a physics point of view. Okay, so maybe I'll just breeze through the other ones. This one is like there's a garbage. You know how if you have a black bag and you fill it with air, it will start to float because of this. So the idea of this one is to try and make one large enough so that you can lift a whole person up, basically calculate the potentials of that. All right. Number 5, electric planes. This is another transport-related one. So to see if electric planes are a viable thing. A lot of people in Silicon Valley are sort of excited about this kind of thing. There's a lot of venture capitalists throwing a lot of money at this. It's supposed to be like, taxi for rich people, right? So they can just go between relatively short distances, but, for example, going from Silicon Valley to San Francisco, maybe you'd use some short distance plane for that. See if this is a viable kind of technology. Another transport one. But this one is suborbital planes. So these are planes that go higher than regular planes. So they more or less go into space, and then they go into orbit, well, almost orbit, and then they come back down. And so this is supposed to be like a much faster way. So much faster way of traveling, much better in some ways than supersonic travel. Of course, we had supersonic commercial planes a few decades ago, but then they were too costly to keep on going. So perhaps we can revive this kind of mode of travel where you can actually travel, much faster than regular planes, which, as most of you would know, just traveling, but planes are fast, but it's still flying to New York from here is quite a painful process, right? So faster would be better. So this is one that I added this year. So I don't know. I should have put some pictures on this one, but so. So you guys can watch the full video later, but there's this type of contraption that some people invented where essentially how it works is that it's like a car, but then there's a propeller that's on it, right? Yeah, and then it's basically a wind-powered vehicle. But instead of it, just being like a sailboat where you have a sail, the propeller is actually driving the tires of the car. Okay? And then the claim is that this thing can actually travel faster than the wind. So if the wind is going at some velocity v, it can actually travel faster than that. It seems completely impossible, right? And so this guy in bed with the UCLA professor that such a thing is simply impossible. The professor was proved wrong. So they could actually build something, and they really could measure something that can go faster than the wind itself. So, they try and explain it in this video, but frankly, I still don't really get it. I don't know how this could possibly work. So the idea here would be to try and work out how that actually works.
Infinite weight with any amount of force on the other side. The catch is its displacement will be zero. Second of all, in practice, there is a propeller efficiency term that is ill-defined when the propeller is not moving through the air.
Okay, so that's that one. Another one is Angry Birds. Okay, well, So you know this game, Angry Birds, you throw a bird and then it hits something and yeah. So, perhaps one of the major uses of, all these equations that you're going to learn in this course is actually in games, right? Because games use a lot of like physics engines, and so whenever you want to make some kind of realistic looking game, essentially you essentially just simulate physics in the world that you're actually recreating, right? Okay, Angry Birds is a bit of a simple example, in this particular article, they actually modified the laws of physics to sort of to make it not like physics that we used to, but physics of a maybe an alternative universe. So the idea would be to kind of look at this and figure out what the real equations of motions are. So it's this sort of game-related thing. That one's changed. This one hasn't. Okay. Well, anyway, that's your topic anyway. So if you don't like any of these, then you can come up with your own topic. But maybe just come to me beforehand so we can just discuss it, see if it's sort of substantial enough so you can investigate things. Okay, and so as I said in the previous lecture, what you'd be doing is to investigate this in groups of 4, and you'll be giving a talk, using PowerPoint, something like this, and explain it to the rest of the class. It would be like just a 10-minute talk, although everybody always goes over time, but let's try and keep it to 10 minutes. And in the presentation, you're supposed to all talk, right? So that you have 2.5 minutes each. Okay, and finally, there will be a brief report that you need to submit, and that will be at the end of the semester. And the assignment grade will be partly based from the presentation and partly from the write-up. We can maybe talk about this later, but I've found that there's a sort of a golden format for when you present something, especially in a sort of a scientific talk. So you tend to have this kind of relatively fixed structure because there's a tried and tested way of communicating ideas to people, and it sort of goes like this. So you first start with sort of an introduction of the general statement of the idea. Often people just start talking about the idea, as if everybody knows what they've been doing for the last, 2 months. Obviously you need to tell them what you're trying to do, and then people, understand, oh, okay, so this is the problem this person is trying to solve, okay, and then this is what you did next, and so forth. So you first start with like what you're actually trying to solve. Then you might discuss the method or the basic idea for what you're trying to do, and then show some details of what you did actually. Most people can sort of manage that, and then finally you summarize. And it's very important to summarize because what often happens is that you're explaining something, and then at the end it's quite confusing and you don't really know what you're supposed to make of everything that you've just seen. So you need to, as a presenter, you need to tell them that this is the conclusion that at least the presenter came to, right? And other things like problems. Anyway, we can talk about that later. Yeah. Yes, and in a science type of presentation, you do tend to include a little bit of technical detail. So, this is not like a TED talk where you just have a slide of like one single object and sort of talk about it for 10 minutes. You do tend to show some nitty-gritty details of actual calculations, equations, things like that. Yeah. And as I said, try to be realistic as possible. After we've decided the groups, then there'll be, I'll send out a schedule I'm going to choose this randomly because everybody, of course, wants to go last, but, you know, fortunately, not everybody, we can't all go last. So I'm going to basically randomly choose the groups, and then it's not, I don't know if it'll be exactly this schedule. Sorry, this is sort of half written, but it will be start maybe in about a month's time. Okay, that's it. Any questions with the assignment? Yep.
You decide the group and you...
Yeah, so I'm going to send a sign-up sheet this week by email. And then, so basically what you'll do is there'll be like group 1, 2, 3, 4, or rather assignment topic 1, 2, 3, 4, 5, 6, 7, 8, 9. And then you put your name in the group or the topic that you want to do. Okay? So you can coordinate with your friends or whatever to go into a particular group, or, you know, you just put your name somewhere. Yep.
You say that you want to arrange our sequence, but if I really want to go first, is that possible?
Oh, sure. Yeah. Okay. Yeah. So if you have a great preference for when to go, I mean, you know, it'll be your kind of a group, right? So in a way, I don't know if your group members will agree, right? But yes, you can send me your preferences.
Okay.
But I don't know if I can stick to it exactly yet.
Okay.
All right. Okay, this one's still not. Okay, so let's continue on with finish off this chapter that we were talking about, measurement. So thinking about standards and units, definitions of length, time, and mass. And I think this is where we're up to before. I don't think maybe we really need to recap so much, so we can just continue on. Okay, this is a little bit, you know, I don't know why this appears in this chapter suddenly, but for some reason they somewhat out of nowhere define density. So density is, of course, you know, well, it's the mass per unit volume of some objects. So some things which are, you know, very dense, things like lead, gold, are very dense materials. Other things are less dense. Of course, you know, gases are extremely have low density. Mass per volume, I think that's pretty much all there is to the definition. And okay, so I think just to finish off this chapter, we have this question, which is a little bit interesting. Maybe you can get together in pairs and do this particular question, okay? So the question is this. So suppose that while lying on a beach near the equator, watching the sunset over a calm ocean, you start a stopwatch just as the top of the sun disappears, okay? So it's sunset, sun's going down, you're lying like, you know, sort of, I don't know, yeah, doesn't matter, okay? You're lying completely on the beach, right? Then you stand, elevating your eyes by a height 1.7 meters, that's how tall you are, and you can see the sun a little bit again because you're a bit higher. You stop the watch when the top of the sun again disappears. And if the elapsed time is 11.1 seconds, what is the radius of the Earth? You can calculate the radius of the Earth just from this. I'll give you a couple minutes to think about it. So get together in pairs. How you guys going?
I think I know here.
Yeah.
Can you find the number?
Okay. Before we talk about numbers, so how did you? What was your logic, or how did you?
Because the 11.1 second will give you an angle.
Right. Okay. So let's write that down. So the angle. Okay. So this way. F. Did you press F1? Thanks. Okay. So how do we work out the angle?
So the angle is a day has 3,600 times 24 seconds.
Right.
And 11.1 over the number times 360.
So 24 hours times 60 minutes.
Yeah,
60 seconds. Yeah. Times by
360.
360. Yeah.
Yes.
Or yeah. Maybe we can do 2 pi. Yeah.
Yes.
Same thing. So that's going to be our angle in radians. Okay. Then what should we do?
And know the two sides.
The what? The side of.
One is R and one is R plus 1.7.
Okay. I see. So what kind of a diagram should we draw? Triangle, yes, but okay. You know, I think in these types of problems, you should draw a sort of a sketch of what's going on. And I was trying to look over your shoulders to see whether you guys had the kind of sketch that I had in mind, but I think many of you didn't quite. So the sketch that I would draw is like this. Like, you know, even if it totally makes sense to you, just having a diagram just makes it just so much easier to understand. So this is kind of the thing that I would do. Okay, so the sun is over here, it's far away, so that's why it's small like this. Okay, and then so the Earth is rotating, and suppose at the beginning the person is lying flat like this, right? So like this, yes? Okay, so if the sun is gonna be setting, so which way should this be rotating? Sort of clockwise or anti-clockwise?
Is it possible?
No, I mean, I guess I'm saying, I'm giving a sort of a, you know, you might say a sort of a top-down view, if you like, because this person's on the equator, right? So, huh? Anti-clockwise. Yeah. So, should be rotating. Earth should be rotating this way, because if it was rotating this way, then you know it'd be heading into daylight, right? This side is nighttime. Yeah. Okay. So. At some time later, well, 11 seconds later, so it's going to be like this, right? And so the idea here is that the line of sight of this is going to just hit the sun like that, right? So that when you're lying down here, you just see the top part of the sun, because, well, that's the last bit of the sun you can see. And then some time later, you're actually in that same line of sight, but you're standing up, so that's why you can still see it. You're lying down at this point, of course, you wouldn't be able to see it. The Earth would be blocking it. Yeah. Okay, so now we can draw some radii. So I think what you were saying was, so we draw maybe one radius like this and another one like this, right? Okay, and then this angle that we were just talking about must be this angle, right? Okay, so now what do we do?
Use the cosine.
Right. Okay, and the height of the person was 1.7 meters, right? So this distance here is h, yes? And so the triangle that we're going to use, I guess, is this one. So what what is the equation that we're going to have here?
R over R plus H because T cosine.
R over R plus H is cosine. Right. Okay. And then it's just a matter of rearranging this equation. So R is equal to R plus H cosine. And then we can just, we want to find R, so we have to factorize this. 1 minus cosine theta, right, is equal to H cosine theta. R is equal to H cosine theta divided by 1 minus cosine theta. Is that what you got? Is that the formula? Yep. Yep. Okay, and then you substitute some numbers. To me, that's just the sort of the trivial part. You know, I almost don't care about the number. That was the hard part, if you like. And what I get was 5 to 18 kilometers. What's the real radius of the Earth? Does anybody know?
6,800.
Yeah, so it's not so bad. Not so bad for a on the beach calculation. Yeah. Okay. What is this? Keep on failing today. And the okay. Playing up today. Might just restart it. Well, it's a bit hard to see, but you might just live with that screen. Okay. Alright, so that was chapter 1. Any questions with chapter 1? Nope. Okay, let's push on. Right, so this chapter is talking about motion along a straight line. So it's stuff like, you know, velocity, acceleration. Okay, so we need to first set up some kind of coordinate system so that we know where an object is. We're not going to talk about anything to do with the structure of the object, you know, so we're just going to basically think about just like a point-like object, and we're essentially just going to talk about, you know, the things like the how fast it's going, and just describe the motion using the coordinates. So we can define position while using this kind of coordinate system here. Some origin, that's basically the zero position of everything, and some direction is sort of arbitrarily chosen as the positive direction, and another the opposite direction is the negative direction. And so we can talk about displacements as changes in the position. So if it starts at some position x1 and ends in position x2, then the change in the position is the displacement, right? So for displacement, there's no information about the path that it actually traveled. So it may well go in some weird path. So say it starts at -2 and ends at plus 3. So it may well, go back and forth, do kind of all kinds of backtracking. It doesn't really matter from the point of view of displacement. Only the final and initial positions really matter. Okay, so that's displacements. Okay, 3 pairs of initial and final positions. Which pairs give a negative displacement? Which one? Oh, sorry, just shout it out, yeah.
Okay, is position just a vector?
Yes, position is a vector, but we're actually just working in 1 dimensions now. So because there's only one element to the vector, it's just a scalar actually. Yeah. So which one is the negative displacement? Which one? Right, C as in answer C, right? Yeah. So B and C are negative because they basically go backwards. This one's going forwards, this one's going backwards. Okay. So we can draw position time graphs. This is a useful way to represent how the object moves. So the vertical axis is position, and the horizontal axis is time. And so, for example, a stationary object is not changing in time, so that would be completely flat. A moving object will have some kind of slope, and essentially the gradient of this will give you the speed of the object. So there's different types of speed or velocity. So we can find a so-called average velocity, and this one is defined in terms of the displacement divided by the time, right? The change in time, difference in time. So in this one, remember displacement didn't really depend upon the actual path of the object, right? So you could have had something that's going forwards, backwards, that's some crazy motion and then ends up at the final position, or you can have something that has a smooth path and they would have both the same displacement. So likewise, they would have actually also the same average velocity. So average velocity is a quantity that doesn't depend upon the actual path of the object. On the other hand, something like average speed does have a dependence upon the actual path. So, for example, well, just to contrast those two cases where one is going in a crazy path from point A to point B, or another one that's going in a smooth, constant speed. So we can distinguish those two in terms of this formula. So you'd have to sort of work out what the total distance that is traveled by each one and then divide by the time. And in that case, these two cases would have a different speed. And of course, the one that is going, back and forth in this, with a much traveling a much longer distance would actually have a larger speed, obviously, because it needs to go from A to B, but it's doing all kinds of funny, backtracking along the way. Okay. So furthermore, there's another type of velocity or speed, which is the instantaneous velocity. In this case, you take the derivative with respect to the motion. And so this will not be a single number for a particular path. At each position, or sorry, at each time there will be a different velocity. So this will be like the slope of this curve at any given time. So here actually it'll be going backwards, right? This has got a negative gradient, so it's actually going backwards. Here it's flat, it's actually stopped. Here it's moving forward. Here again it's stopped. Here it's going backwards. This one is always moving at the same instantaneous velocity. So there's different, slightly different definitions of speed depending on sort of what you're interested in, basically. You know, if you're interested in sort of like how many calories you're burning up in your run, obviously this is actually the relevant one because, you know, how many calories you're going to burn up is dependent upon that. But if you're only interested in, you know, how you achieve, you know, how you get from point A to point B, and you don't really care that you, you know, whether you were on a taxi or a plane or, you know, you walked, then, you know, you might use this one. And obviously, if you're looking at a car speedometer, then this is the one that you're actually looking at. Okay. Following equations give the position x of a particle in 4 situations. X is meters, c is seconds. Okay. In which situation is the velocity v of the particle constant? Okay, so let's do that one. Just shout out the answer if you know. Yep. Yeah, number 1, yeah. So that's, I would say that's correct. Actually, but maybe also number 4, right? Yeah. Well, 0 is a constant, but yeah. Well, I think they're both acceptable answers, I would say. Yeah. In which is v in the negative x direction? Right. Yeah, right. So we take the derivative of these ones. If you take the derivative of this, the velocity is just simply 3, and as we discussed, the velocity of this one will be 0, but they're clearly not negative. This one, if you take the derivative, it will be minus 8t, and it doesn't really say, does it? T is greater than 0. Yeah, so if t is greater than 0, then that will be negative. This one, you take the, this is 2 times t to the minus 2, and then so if you take the derivative of that, it would be minus 8t to the power of minus, t, so x is 1, so this is t, so v is minus 8t minus 3. Don't forget F1. Hi. Okay, thanks. So in this case, because t is again greater than 0, it will be negative. Okay. All right. Acceleration, which is the, how fast your velocity is changing. So, or how quickly is your speed going up. Right? So we basically have very similar looking formulas, except everything is velocity, not position. So likewise with average velocity and instantaneous velocity, we have also average acceleration and instantaneous acceleration. So the formulas look basically the same. You, in the case of average acceleration, you look at the velocity difference, the start at the end. divide by the change in the time, that's your average acceleration. So the units would be, for example, meters per second squared. Instantaneous acceleration is the second derivative of the position, or again, the derivative of the velocity. By the way, I will use calculus in this course because I think it's just, well, it's much actually easier. So some courses try to bypass calculus somehow, but I really think it's actually harder to do it that way. So anyway, it's not, we're not doing any calculus that's probably any more difficult than something like that. Now here's a sort of a rule of thumb, which is maybe not too obvious. If the signs of the velocity and acceleration particle are the same, the speed of the particle increases. If the signs are opposite, the speed decreases. Okay, which seems a little confusing when you look at it, but actually it's pretty obvious. So if it's, so if we're looking at some object moving with some, say, positive velocity, right? And acceleration means that the velocity is either increasing or decreasing. So if the acceleration is positive, then this particle would have, well, added some velocity because this acceleration is positive. So it's adding to a velocity, right? So the velocity is going to become even larger than a minute ago, right? So if the signs of the velocity acceleration are the same, then the particle is going to be increasing. So this is positive, this was positive, and so this is going to be increasing speed, right? But if we look at the opposite situation, where the velocity is negative, I'm going to rub this out. So it's going this way, but then the acceleration is still positive, right? So imagine this was going velocity of minus 10 meters per second, right? But if the acceleration is positive, it's still adding a velocity to it, right? So this is, say, a negative number. This is still adding some velocity, but because this change in velocity is going to be a positive quantity, and this was originally a negative number, so it's like minus 10, I suppose this is like going to be 1, be minus 9. So actually it's actually braking because it's slowing down in terms of the speed. So the acceleration always has a sign that you have to sort of think about. Likewise with the other way around. Okay. So there are 3 different types of graphs, I guess, that you can draw with respect to this kind of thing, position versus time graphs. That's the one that we already encountered. That's the one at the top there. Yeah. Velocity time graphs and the acceleration time graph. So these are basically just related to each other by the derivative, right? So this is the one that we encountered before. So here is the position, and if it's, for example, in this graph, it sort of starts out flat, right? That means it's not moving because the gradient is 0. That means it's not moving. Starts to speed up, and then here's a flat kind of region. So it's going to sort of speed up and then move at a constant velocity in the positive direction. And then it starts to flatten out again. which basically means it's going to slow down. So basically what this would describe is something that is here, it speeds up, it moves constant velocity, slows down, comes to a stop. So if we wanted to work out what the velocity time graph is, then what you do is just take the derivative of this curve. So just taking the derivative. So over here, where it's kind of speeding up, if you take the derivative of this one, then it will be, well, it's kind of speeding up, so the velocity is going to be increasing. So take the derivative of this curved part, then it will be like this flat line here. In the region where it's like a constant velocity here, well, it's a constant velocity, so it will be flat line like that in the velocity time graph. And then when it's slowing down, basically this will be ramping down like this. So we can view it sort of in terms of the speed of the object. And then in terms of the acceleration time graph, we take the derivative of this one again, and the derivative of anything that's constant is 0. So anything, any region like here and here, here, the acceleration is 0. But where there's a slope, this will be, this will have a positive value, and this is a negative slope here, so that will have a negative value. So it's kind of 3 ways of viewing this this kind of object. And in practice, actually, the velocity time graph is kind of most useful. Well, I don't know, maybe that's subjective, but it's most useful because actually things like we'll come to this later, but for example, the position you can work out actually using by finding the area under the graph, because going the other way you basically can integrate, right? So if you integrate this graph, then you'll get the position time graph. If you integrate the acceleration time graph, then you'll get the velocity time graph. So it's kind of most useful because by integrating you can get this one, and by differentiating you can get this one. But from this one, it's sometimes a little bit hard to imagine what the second derivative looks like because it's not just a slope, right? So, you know, in our minds we can do one step, but doing 2 steps is a little bit too much for the human mind, right? Okay. All right, so let's do this one. So wombat moves along x-axis. What is the sign of its acceleration if it is moving in the positive direction with increasing speed? All right, so it's moving positive and increasing in speed. Acceleration is positive, right? Yes, positive. If it's moving in the positive direction, but it's decreasing in speed, which way is acceleration? I heard some answers, but it was, sorry, what was it? Negative, yes. In the negative direction with increasing speed, I think, yeah, people said negative. And in the negative direction with decreasing speed. Yeah, positive, right? Okay, so here comes our 5 magic equations for constant acceleration. Okay, so you've probably seen these equations before? Who's seen these equations before? Yeah. Okay, so I think most of you, but let's go through them again. Okay, so this is kind of classic, you know, physics, problem solving. You can certainly just quickly derive them, but often in problem solving it's useful to commit these more or less to memory and then just quote them and then apply them to different types of problems, right? But let's go through the derivations anyway. So we're going to look at a particular case where acceleration is constant and we're just moving in a one dimension, right? Okay, so if we're moving in one dimensions, then basically what we're saying is that this A, which is F1, please. Thanks. Okay, so this thing is going to be a constant. So this is a pretty big assumption in a way, right? Because it's not always the case that acceleration is just going to be constant. But there is a particular case that is very important in our kind of context, which is that on Earth, the gravitational acceleration is basically constant. It's basically constant because for the stuff that we're doing in our daily lives, the Earth is so much bigger than us, so that we can just pretty much consider it a constant. Obviously, if you're doing something like space travel, then you have to think that gravitational acceleration is not a constant. But for what we're doing, it's very, very good approximation that it's constant. So this is why it's so useful to look at this particular case. It's mainly applied to cases where it's, acceleration is a constant, even though that's usually a big assumption, right? So, okay, so for this particular case, just this one assumption basically simplifies a lot of the analysis so that we can just more or less solve this kind of scenario pretty much with a set of simple equations like this. Okay, so let's go through the equations one by one. So let's call the first one there equation 1, so the 2.11, equation 1. So how do you get that one? Well, essentially just kind of invert this equation. So if acceleration is a constant and the velocity, acceleration is the derivative of the velocity, then we can find the velocity by integrating the acceleration. This is just the acceleration is just a constant, and if we assume that we're going to start at time equals 0, then we're going to have AT plus what's the constant? Well, okay, so maybe I should how should I do this? Okay, well, maybe that's good enough. Maybe you know what I mean. And this constant we can find because at t equals 0, let's say that the initial velocity is equal to v equals 0. So that means that when we do the velocity, we'll have at plus v equals 0, and then we have our initial condition like this. Okay, so essentially we can just invert the derivative on that. For the second equation, we basically do the same thing. We can start with this one. So we know that the velocity is the derivative of the position. And we just worked out that the velocity is at plus the initial velocity. So we can find the position just by integrating the velocity. So we integrate that, we'll have half at squared. Again, we have a constant. And in this case, what we're going to do is we're going to say that at t equals 0, the initial position is x equals 0. So this means that our constant, integration constant there, should be equal to x equals 0. So basically, so that means that this thing here is x equals 0. And so we can just rearrange the equation, and so this is our equation number 2. Yeah. I don't know. Either it's everybody's seen it before and bored, or people are confused. I can't tell. It's fine. It's fine. Okay. I'm going to assume it's fine. Okay. All right. So actually, those two equations are really in a way, the essentials of all you really ever kind of need, really, because we've now related velocity to acceleration, and we've also related, but here there was no position, so we kind of really need another equation involving position, right? But now we've got another equation with position, right? So in principle, that's actually it. But it's handy to write the equation in a couple of other different ways, because if you notice, actually over here, you notice here, so this, let's look at the 5 variables that are involved. The 5 variables that are involved are, well, basically x, the a, so position, velocity, acceleration, but we've also got time, and is there another one? What's the other one? Oh, I see. Okay, well, initial, okay, maybe a slightly weird way of thinking about it, but initial velocity would be another one, and okay, well, let's stick to the way that it's written. So x minus x0, which is the displacement, velocity, acceleration, time, this one. So there's kind of 5 variables involved, and these equations will link these quantities together. And if you notice, for example, in this first one, it involves velocity, the initial velocity, acceleration, time. So it's an equation where this one is missing. The position or displacement is actually missing. Right? Here, the one that's actually missing is the final velocity. This is the velocity at the end of the movement. Yeah? And what you can just do is to algebraically eliminate the other 3 variables. So we can basically eliminate time just by substituting like equations 1 and 2 into each other, and we can eliminate time from that and make it like another equation. So that's like third one. We can also eliminate acceleration and get this one. We can eliminate the initial velocity and get that one. So Yeah, so we can do that. I think I'll do that next time. I don't have enough time, but basically these 5 central equations for motion are derived in that way. Okay. All right, then we'll wrap it up there. I'll send up the sign-up sheets for the assignments this week, so please do that, and see you next week. Faster. Yeah.